right, so in the last video, we learned the insertion sort algorithm, and you saw the implementation, or at least one implementation. And I said that insertion sort is a quadratic algorithm, and it is, but if the sequence of values that we're sorting is nearly sorted, then insertion sort runs in almost linear time. And it does that because it doesn't have to do as much shifting. Think about it. If most of the values are already sorted, then only a few values will actually have to be inserted into the sorted partition, and the amount of shifting will be reduced. Now, a computer scientist named Donald Shell realized that if we could cut down on the amount of shifting, that insertion sort would run a lot faster, and so he came up with something that's known as the shell sort algorithm, and that's what we're going to look at in this video. So how does shell sort work? Well, it's a variation of insertion sort, and what it does is insertion sort chooses which element to insert using a gap value of 1. So every time insertion sort runs, it picks off the first unsorted value, and then it compares that value to its neighbor, and it keeps shifting the neighbors to the right until it finds the correct insertion point for the element that it's inserting. Shell sort starts out using a larger gap value. So instead of comparing elements to their neighbors, it compares elements that are farther apart from each other in the array. And then as the algorithm runs, it reduces the gap that it's using. And the goal is to reduce the amount of shifting that's required. So as I said, as the algorithm progresses, the gap value is reduced. So shell sort traverses the array with a certain gap value, and after it's done its first traversal with the initial gap value, it decreases the gap, and it does it again. And it does this, and this is very important, it keeps reducing the gap value until the gap value is 1. Now when the gap value is 1, we're essentially doing an insertion sort. So the last iteration of the gap value will actually perform an insertion sort. But at that point, the array will be more sorted than it was at the beginning. And so essentially what shell sort does is it does some preliminary work using gap values that are greater than 1. And that preliminary work puts the elements in the array and perhaps closer to their sorted positions, and then at the very last iteration, when the gap value becomes 1, it does an insertion sort. But that final insertion sort will be working with values that have had some preliminary sorting done on them. And because of that, there'll be a lot less shifting required. So one question is, well, what do we use for the gap value? How do we figure out what to start with and how to reduce it? And you're going to see that there's a ton of theories about this. We're going to go out now to the Wikipedia article about shell sort. So here we are at the Wikipedia article that I've linked to in the resources, and here's a table with different initial gap values and how to reduce the gap, what sequence of gap values to use. And as you can see, there's quite a number of them. The important thing to note is that the way that you calculate the gap can influence the time complexity. And so here we have a time complexity column, and depending on what gap we're using, the time complexity is different. We have a logarithmic time complexity here. Here's a quadratic time complexity. And so the gap value you choose can influence how many steps the algorithm requires, so keep that in mind. Let's go back to the slides. Okay, so there are a number of ways we can calculate the gap value. One really common sequence is used for the gap value, and the gap is also called the interval, is the Knuth sequence. I think that's how it's pronounced. I've never pronounced it before, said it out loud, so I don't know if the K is silent or not, but it's the Knuth sequence. And this says that we calculate the gap using 3k minus 1 over 2. And the initial value that we want to use is based on the length of the array. What we want is we want to use the value of k that's going to calculate to a value that's as close as possible to the length of the array without going over. And so if we had an array of, let's say, 20 elements, we would want to start with k equal to 3. If we were to start with k equals 4, the gap would be 40, and that's greater than the length of the array, so that won't work. And so when you want to use this sequence, you want to start with the value of k that's going to result in a gap value that is as close to the array's length as possible without going over. Now, in the implementation I'm going to show you, we're not going to use this sequence, but it's a common way of calculating the interval or the gap, so I thought I'd show it to you. We're going to do something simpler than that. So what we're going to do is we're going to base our gap on the array's length, and we're going to initialize the gap to array.length over 2. And then on each iteration, we're going to divide the gap value by 2 until we hit 1. Now, our array only has 7 elements in it, and so the first gap value is going to be 7 over 2, which is 3, and then the second gap value will be 3 over 2, which is 1. So we're actually only going to have 2 iterations for this array. So on the first iteration, we'll use a gap value of 3, and then on the final iteration, and this is always true for shell sort, the gap value will be 1, and at that point, we'll be doing an insertion sort. But because we've done a previous iteration and we've moved some of the elements around, some of the elements will be closer to their sorted positions. So let's go through this. So we're going to start with a gap value of 3 because we're going to use array.length over 2. We're going to initialize I to the gap and j to I. And as we did before with insertion sort, we're going to save the value that we want to work with into new element. And then what we do is we compare the element at index j minus gap, so that will be 3 minus 3 is 0, with new element. So our gap is 3, and we're starting with element 3, so we're basically want to compare it, because the gap is 3, we want to compare it to the element that's 3 positions away. And so we compare 7 with 20. 7 is less than 20. And so what we're going to do is we're going to assign 20 to where 7 was. So instead of doing what we were doing with insertion sort, which is we're comparing to the neighbors and shifting up 1, we're comparing using a gap of 3, and we shift by 3. And so 20 has been shifted up 3 places. And then we're going to set j to j minus gap, which is 0, and we've hit the front of the array at this point. And so what we're going to do is assign new element to position 0. So what we've basically done is we're kind of doing an insertion sort, but we're using a gap of 3. So what we're going to want to do next now is move I to 4. And j becomes I, which is 4. The new element is 55, and we're going to compare 55 to 35 because that's 3 elements away. 55 is greater than 35, so we don't do anything. Everything remains as it is. And now I will come to will be 5. J will be 5. We're going to compare 1 to minus 15 because minus 15 is 3 elements away. Okay, so there's nothing to do because 1 is greater than minus 15. And so now we're going to move to minus 22. And we're going to assign that to new element, and we're going to compare it to the element that's 3 positions away from it. And minus 22 is less than 20. So we're going to assign 20 to position 6. Now at this point, we're going to subtract the gap from j, and then we're going to compare minus 22 against what's at position 0, because we want to go 3 elements away again. Minus 22 is less than 7, so we're going to shift 7 into position 3. And at this point, we've hit the front of the array. There are no more elements to compare minus 22 against, and so we assign minus 22 to position 0. And at this point, we've hit the end of the array, and so we have finished our first iteration with gap equal to 3. Now notice that the array is more sorted now than it was before. And we've moved minus 22 all the way to the front of the array, and we did that with 1 assignment. And so in insertion sort, pure insertion sort, at some point we would have had to have shifted minus 22 down, or rather in the implementation I showed you, every single element would have had to have been shifted up to make room for minus 22. But in this sort of pre-sorting phase, when we're using a gap of 3, minus 22 was moved very quickly down to the front of the array. We've also moved 20 closer to its sorted position. 20 started at the front of the array, and now it's only 2 positions away from where it usually ends up in the sorted array. So you can see how doing this preliminary work before we get to insertion sort will cut down on how much shifting we have to do. So at this point, we're going to update the gap. We're going to divide 3 by 2 and we'll get 1. And so at this point, we will actually do an insertion sort because the gap is going to be 1. So we're going to be comparing everything to its neighbors, and when we shift, we're going to be shifting up by 1. And so at this point, we'll do an insertion sort, but we're doing an insertion sort on an array that has had some preliminary work done on it. And so there's going to be a lot less shifting, and that's what shell sort is all about. So shell sort is an in-place algorithm, just like insertion sort. We're working within the original array. Now, as you saw, it's really difficult to nail down the time complexity because it's going to depend on the gap. It's going to depend on the method that you're using to choose the gap. In the worst case, it can be quadratic. We saw that when we went out to the table on Wikipedia, but it can also perform much better than that. It doesn't require as much shifting as insertion sort, so as I said, it usually performs better than insertion sort. However, it's an unstable algorithm. Insertion sort is stable, but shell sort is unstable, and you can see why. It's because in the pre-insertion sort phase, when we're comparing elements that are far away from each other, it's very possible that if we have a duplicate element, the rightmost element will be shifted in front of the leftmost element. So the fact that we're examining elements that are further away from each other can lead to the relative positions of duplicate items not being preserved. Now, one last note before we go to the implementation, you can also improve bubble sort using shell sort, and it would be the same type of idea. You would use a gap interval. Remember, in bubble sort, we're always comparing elements to their neighbors, and then we're swapping and bubbling elements up. Well, it's the same sort of idea. So in bubble sort, if we use a gap of 1, that means we compare to the neighbors and everything gets swapped up 1 position. Things get bubbled up. If we do some preliminary work, and in this case, rather than just shifting elements, we'd actually swap them, we can improve bubble sort. So you can apply shell sort to insertion sort and bubble sort and improve both algorithms that way. With insertion sort, you're cutting down on the number of shifting, and with bubble sort, you'd be cutting down on the number of swaps that you have to do. Okay, so that's it for taking a look at how the algorithm works. Let's implement it. I'll see you in the next video.